Привет всем. So I want to talk today about MobX, unique symbiosis of predictability and speed. That sounds a bit abstract, but basically I want to talk about how this idea is not entirely new, but also like how it's different from how it's done before. Because I noticed like in the past, I got a lot of questions about it, and so first we're going to dive into the general idea, and then also we're going to try to make a deep dive on how it actually works and build our own version. So an interesting question is, what does this product have in common with this one? I think you know both of them. This is the new version of the web client of Outlook, and this is Battlefield. And what they have in common is that they're both using MobX for state management. And that might be surprising, but I hope that during this talk it becomes more clear why. And so we'll dive in roughly 5 subjects. I'm going to do a very quick recap on reactive programming, and then I'm going to talk a bit philosophical about mutability and observability and immutability. And then we're going to do the fun stuff, which is how does MobX work and some live programming. So first wow, that color. First a quick recap on reactive programming, just to set the context. And so I know most of you are probably familiar with this concept of having pure functions. And so the idea of a pure function is that its output is only and entirely depending on the input arguments, which are immutable, and also that the function doesn't have any side effects. And so when you have those two things, you can do something very funny, and it is you can basically replace the function invocation immediately with the output of that function. That has exactly the same semantic meaning. And it's really cool, because that means that you can memoize stuff. Entirely different question. Who likes taxes? Paying taxes. Please raise your hand. Nobody, right? Yeah, so yesterday I landed at the airport. And between the airport and this hotel, I already learned 2 ways in which to fool the Russian tax system from my cab driver. So I'm pretty sure you don't like to pay taxes. But on the other hand said, we kind of need it, because like there's a lot of things we need to maintain, like roads, and they're really beneficial for us all. And so that's kind of why we live with paying taxes. And the same is a bit true for side effects. So I have the same function as before. This time it's side effect full. It prints a message. And that means I can no longer substitute its invocation with its result, because then the message wouldn't be printed anymore. And so in every application, we do need side effects for rendering, for making network requests, doing file operations, that kind of stuff. But also, side effects are annoying because they're hard to test and verify. They change things outside your application. We don't like them. But sadly, it's basically impossible to build a meaningful application without side effects, because then it cannot have any output or change the world. So what would be the meaning? Let's take a quick quiz about pure functions. So here I have a function, and my question to you is this function pure or not? Given a set of to-dos, it computes how many of those are not done yet. So who votes for this is a pure function? I see some hands. Yes. Who votes for impure? A few less. I basically would say you can't tell, because it's going to depend on whether that collection of to-do items is immutable or not. So if this function is immutable, it means that any next invocation could immediately be substituted by its result, which is great. If it's mutable, you can't do that. Then any next invocation would depend on the internal state of the to-dos object. And so if it were immutable, that would be a really cool property, because we have this memoization. But on the other hand, this collection of to-dos, like conceptually, is probably going to change in your application over time. So the question is, would it be actually meaningful to memoize this function? Because probably in the future, you're no longer interested in the amount of to-dos left in specifically this set of to-dos, but in the current set of to-dos, whatever that may be. So either to-dos is mutable, or the collection of to-dos lives somewhere else where there is state. There's always some state somewhere describing what our current set of to-dos is. In other words, to have state, you have to have mutability. You can't avoid it. Can't avoid it. Without mutability, it's basically impossible to build anything meaningful. Then you just have a static site. So let's take a more philosophical view on it, like not technical, but like conceptual. So generally, we say that like facts are immutable. Like yesterday, I landed at the airport. That's something that happened. It's immutable. But the current state of a thing, they're not a fact. So whether I am in St. Petersburg or not depends on the moment you ask it. Like today, it's true, but next week, it's not true. So the state of a thing only becomes a fact when you ask about the state on a specific time. However, frontends are mostly about communicating, storing, and chasing like the present. That's what we usually are interested in. So I think it follows from that like sometimes shoehorning stateful things in immutable data structures kind of creates those impedance mismatches. Because technically we make them immutable, but on a conceptual level, we say things like we toggle it or we move it. These are all verbs which describe a state change. And so where do you need mutability? Basically there where you can have where things have an identity, where you can refer to them. So not everything does have to be mutable, like even on a conceptual level not. For example, your address or coordinates on a map or something, they're just like stupid facts. You don't refer to them explicitly, you don't name them. What my address is a property of me that can change over time, but the address itself is just an immutable record. So that being said, mutability and side effects, we generally consider them the root of all evil. And I think that's correct because that introduces always complexity. That's where things typically go wrong. Nonetheless, they are at the heart of every valuable process. You do need them in the end. You just want as few of it as possible. Sometimes I hear people talking about immutable state, so that's an impossibility. State implies mutability. That's what the word means. The only question we have is like, are our values immutable or not? And so state management is in that sense all about controlling the mutability and the side effects in an organized way so that we can control it better. Then what is reactive programming precisely? Reactive programming is just about controlling this concept of having side effects. I really like this definition by Heinrich Apfelmus. He said, the essence of functional reactive programming is to specify the dynamic behavior of a value completely at the time of declaration. That sounds a little bit fake, so let me explain it. This is an example from the RX documentation. And so here there is a button, and this application keeps track on how many times it is clicked, but it also like debounces it every second. And so there's quite some state going on, but also quite some side effects. So this handler is really impure. It relies on state enclosure. It has side effects. And so reactive programming paradigms allow us to organize it better. So for example, with RX, we could describe it differently, where we have a declarative notion of throttling and counting. And so there's still a side effect. It's just confined in a much more smaller place. And that allows us to better control it. and the rest of the stuff is way more pure than it was before. So I now want to go a little bit deeper on this immutability and observability and mutability concept. In the beginning of the year, React 16.7 came out with hooks. You've probably heard of them. And I kind of really like this tweet by De Kietse. He basically tried to use hooks, and I was super happy. And then in the end, he concluded, no, because I started worrying about optimization again. Again, I have to think about how to optimize my application. And I just want to show you what he means with that in a small demo. So here I have a little demo application. It's pretty simple. It's just a bunch of circles connected with lines, and I can add a few more. And so that's basically the entire application. It's not super interesting in that sense. But let's look a little bit about how it's built up. And the thing to notice is the highlights you see, those are components being re-rendered. So basically, the entire application is re-rendering over here, whatever I do, which is not good in general. And so if I look at the state of that application, it roughly looks like this. So there's a state object. It contains circles. It contains lines. The circles have coordinates. The lines, they just connect two of those circles. And of course, the point of this application is that when I move a circle around, the lines have also to be updated in the UI. That's the hardest part here. And so I implemented this application pretty simple. There are 5 components: app, circles and lines, which render circles and lines, and circle and line itself. I'll show them in a minute. And so I create some states based on that initial state. And that state is going to be passed down to my entire tree, so to the lines and to the circles. And so the reason why React is re-rendering so much in this application is because it cannot make any assumptions about what state is. So it will assume, by default, it is a mutable object. And that means that if I, after calling a dispatch, store a new state, it needs to pass that data down to the entire component and cause all the components to re-render. Because it might have some chains deep inside it, which might be relevant for some child. So here's, for example, the line component. And so a line component depends on the line, but also on this collection of circles, because it needs to look up the coordinates where it starts and where it ends, based on the circles it's being connected to. And then it renders the SVG path based on that. So because any chains deep inside the line or circles might be relevant for this component, as far as React knows, it will always render all the circles, the entire application. Because over here the state changed, so everything might need re-rendering. So that's pretty bad. But we wrote this as a reducer, and we know that the state we're having here is one big immutable value. So we can leverage that to optimize the thing. Oh, great. Hi, WhatsApp. So what we can do is we put a memo on each of those components. So now we're going to leverage the fact that those data structures are immutable, which means that if React gets passed in the same reference to an object, then it doesn't need to re-render. And so let's try that. And actually, I think this result is a little bit disappointing, because most of the application is still re-rendering. I mean, some things are not re-rendering, but most of it is. So all the lines are re-rendering on every drag. So let's check why that is the case. So if you go back to the diagram, the state of the data that this circle component gets passed in doesn't change, so it doesn't re-render. However, the set of circles changes, and the set of circles is relevant for every line component. So every line component has to check again whether his circle was maybe changed and re-render. And so basically, when you look at the reducer, there you can see how that is caused. Because if I move a circle, that affects my collection of circles and then basically my entire state. And so because there's a new collection of circles, I have to pass it down again. So can we optimize that? Yes, there are several ways to optimize and solve this problem. So the problem we're now having is that we derive those coordinates in the render function. So what we could do is we could denormalize the data and store the coordinates of all the circles also in the arrows themselves. And then have the reducer take care of updating all the connected lines. I think that's in general a bad idea, because then you're like duplicating data, and it becomes very easy to forget to do that somewhere and mess it up. Other thing you could do is to move that lookup of the connected circles to the parent, which is re-rendering anyway, and have that logic over there. And that means that, like, if the two circles connected to the line didn't change, then the component doesn't re-render either. Also an approach I don't really like, mostly because it moves this logic to the parent, while it's actually totally unrelated to the parent. But there's a better way to solve this, and that's to optimize the memoization. So I have a small snippet here because it was too long to remember. And so when I have my line component, I can pass a second function to the memoization function and give the conditions for the memoization. So what I'm going to tell it is basically if the previous line is the same as the current line, or the next line is the same as the current one, and the circles it connects to is still the same object, both from and the to, then you can still memoize this result. So I've now handwritten a better memoize function to make sure that it doesn't update too much. And so if we take a look at it, if I now move a circle, we see that now only the impacted lines are redrawn and the others aren't. So this is way better. So why was the Kitze still complaining? The reason for that is basically that we just did that, is that we had to think a lot about how to optimize this component, where we can memoize, how we should memoize, what properties we should inspect. There's lots of thought process going in here. But at least like the re-render graph looks much better now. So only the relevant circle and the relevant lines are re-rendered. The rest is left alone. Now let me introduce you to this concept of observable state. Here's a small example of MobX. Is this readable for everybody? Yeah, not small. So what it does is we have some state, we have a side effect, so basically this is our UI printing to the console, and we change this state over time. And now nothing is really happening, the auto run isn't running, the side effect isn't running again because nothing did impact the side effect. Now if I change this application a little bit, it will start ticking whenever, no, that's the wrong button, the state changed. And so it automatically determines that simply by using that state, it has to update our UI, simply because I'm changing the state. So that's MobX in a really brief nutshell. So let's change our application to use MobX instead of immutable data. So I'm going to import a few things. Use state. And so I'm now going to initialize state once, and I just keep it at the initial value because it's immutable. I never need a new one. So I'm grabbing that same initial state. I'm just going to convert it into an observable. And then I'm going to my reducer, and I'm going to rewrite it a little bit. And so basically what I'm going to do is I'm going to say like state circles at specific ID. Its x coordinate is going to be incremented by x. So I'm now only going to modify that circle because it's allowed to be mutable now. Then I return. I throw away the rest of the logic. And then over here I'm going to do the same thing. So I create a new circle. And a new line. And it connects to the circle we just created. Now, please note that this isn't a reducer anymore, technically speaking. I just leave it this way to not have to rename everything. And so instead of in the callback, I'm now calling my reducer. I pass in the current state, and that's very same action description. So that's that. Then I'm going to replace those memo calls with the observer we just imported, except this one, because that's an import. So we don't have any memos anymore, we have observer instead. And also I'm going to throw away this optimization function. Where's the save all button? So we save it all, and now we have the same application again. But the interesting thing is, it's now doing the optimized stuff. So it's precisely updating what is impacted, even though we didn't optimize anything by hand anymore. And in fact, if you pay a lot of attention, then you see it's even a little bit better. So the important thing is that we introduce observer, which connects the component automatically to any state that was relevant. And if you look at the render graph, actually it has become slightly better because even the parent components don't need to render anymore because the things they were looking at didn't change. If I move a circle, it doesn't change the collection anymore. And so basically now I got all the optimizations for free. So the interesting question, of course, we want to answer today is like, how is that possible? Anyway, just for a random picture in between. So before, we were able to optimize our components by using memoization. So why can we memoize it? Well, basically, the reasoning is this. If the data coming in is immutable, that means if the line and the circus object are reference equal to what we saw before, then we also know for sure that they're deep equal. So there's no need to re-render. Now, with observer, the story changes a little bit, but in a surprising way. If you look at how observer is implemented, it's actually still using memo. And that's surprising because the data can be mutated deeply. But it's also wrapping the rendering in the auto run we saw before that updates like the console output. So now we can try to apply the same reasoning. So why can we still use memo over here, even though the data is mutable? That's surprising. Well, because the thing we now know, if line and circles are still reference equal, they might have changed. But if they have changed in any relevant way, that would have been picked up by this auto run. So the component itself from the outside in doesn't need to compare about it. So it can still build out by using the memo. And if there was actually a change deep inside it, which was relevant, then this auto run would have picked it up. So that is why that works. And the interesting thing is, like, once you do that, the tracking, it actually doesn't matter at all anymore where the state lives. So you can even put a state entirely outside the component tree, store it somewhere else, test it first before you write your UI. No need to mount components to test it. And you can make your UI even dumber than it was before. In other words, for things that conceptually change over time, mutable state is the worst thing you can have. Because like, if something's mutable, you need to re-render everything. So better it is to have immutable state, because then you can benefit from the referential equality if things didn't change. But even better is to have observable mutable state. If it's mutable, but you can like observe it at the right place, then you're even in a better position to optimize. So how does that work behind the scenes? Well, the easiest way is usually to just demonstrate it. So I built a super mini UI. And basically, it's very simple. It has like one to-do object, and when I toggle it, it updates. And if you look at the code, this is what it looks like. I have an auto run which renders my UI, so that's the HTML, so that's like my React component. When I click the handler, I toggle this concept of a box. And a box, it takes responsibility of storing a value, and it provides the capabilities to subscribe to its changes. And so now I'm using MobX for this demo, but let's remove this and implement our own versions. And so the important things here are box and auto run. And so box, it takes some initial value, and auto run, it takes some function it should track and run again when needed. And now there's one interesting piece of state, and that is the concept of the currently running thing, and that stores the function that is currently being tracked by MobX, and which we want to build a dependency graph for. And so when we create a box, the first thing we do is like we capture the initial state in the closure. And then we're going to return a little object. And that little object, it has a getter. And when we get a value, we check if there's something being tracked currently. If that's the case, then we link the two together, so that the system knows, like, this box was used by that side effect. And when we've done that, then we just return the value. And then we have a setter, which is pretty straightforward. It updates the value stored in the closure. And then we're going to look at all the side effects that were related to this observable. And we're going to reset the collection of observers. But we're also going to run them all. So this, in one line, empties the set, but also calls the method run of all of them. And so this is the very core implementation of a box. It stores a value in a closure, there's a getter and setter, and can store the relationship with a thing that's currently running. Now that auto run, that takes a function, and it has some internal administration, and we call it a reaction for now. And one thing it stores is all the observables it is using. So we have like a two-way relationship now. Boxes remember which side effects they are being used by, but also the other way around. And it has a method to run the function. And so what it does, it puts itself on that currently running variable that we introduced before. It resets its initial collection of the things it's observing, and then it simply calls the function. And now when that function is called, it starts running, and during this execution, it might be reading from one of those boxes. So it might be calling one of those cat methods, and in that case, the relationship is established. So after it's done running, we're simply going to take a look at all the boxes we did use during the run. And what we then do is we basically subscribe to all of them. So this makes the connection back. Then we reset this variable again. And then the only thing left to do is to run that side effect once to establish initial connections. And so if we try this, then we basically, we're updating one of the boxes, and then the side effect should run automatically based on usage. And if we try this, then that works. So this is basically, without any optimizations, this is the core of the whole reactivity system in MobX. Now, usually, you don't see those boxes because we were using like observable before. So let's re-implement observable as well. I'm going to change the application a little bit. So it's still the same application, just now I have to do object, and I passed it some properties instead of, and then I can just like assign a new value and read values instead of using those getters and setters. And basically what observable is doing is it's actually just creating a new object which internally stores an observable box for every property. And so we loop over the original object, and for each of the properties in it, we create a new box. Actually, this is nowadays done using proxies, but this is usually the version that's easier to explain. And so in the resulting object, we create a getter and setter for every one of those properties. And we simply redirect them to the boxes that are stored internally. And so observable is in that sense just syntactic sugar around those boxes. I'm typing so fluently. And normally this process is applied recursively. And so now we basically have implemented also the nice API of observability. So we're really like interacting with objects the way we used to when we're using observable objects. So that is basically what MobX is doing. It's creating connections between observable values and side effects. And you can conceptually think about an observable object as an object that has a reactive stream for every property. Except it's way more efficient, because if you, I don't know whether you noticed, but like there's no actual subscribe concept. There's no callbacks being set up or something. No, it's just a two-way pointer array, which is really cheap to have, and you can easily have millions of those without any problem. So that is the core of it, and I hope you're following on so far, because then it means that we can now take a little bit deeper dive into the exact semantics of the thing. So we've seen now how observables and autorun work. And there are only two interesting concepts left in MobX. And I'm going to explain them to you by showing the behavior. So here we have a different demo, and we have a store, and it has a collection of to-dos, and it has also keeps track of how many to-dos are not finished yet. And so to calculate that, we use an auto run, and just to make sure that we see when it's computing, we print computing, and then we compute stored unfinished from the to-dos in the store. And then finally, we print the amount of to-dos left. And then as a form of testing, then we toggle the first to-do from false to true. Now, so my question is, if I run this code to you, and please raise your hands, how many things would you expect it to call to print computing? How often will it compute this stored unfinished? So who says 0? 1? A few ones. A 2? A few 2s. More than 2? Let's check it. So the 2s have it. The reason for that is like we run it already one time, this side effect when we start it, and then when we change the done thing, we run it another time. Now I could change it another time. No, I'm first going to change something else. So if I print hi over here, what will be printed first? The amount of to-dos left after changing the done, or hi? What would you expect to see first in the output? Who says hi is first? Let's check. No, hi comes second. So this is quite different from a lot of reactivity systems. But in MobX, every side effect is immediately executed after the change. So it means that you can trust that the side effect did happen immediately. So there's no interleave or async stuff going on there. OK, if that is true, then if I duplicate this line, how many times would you expect it to print? Who says 3? 1, 3, 2s? A lot more 2s. Yeah, the 2s have it. Because this doesn't really change the value anymore of the unfinished to-do count. It will remain the same, so it doesn't need to execute that side effect. Let's remove those. Now I'm also going to disable this printing. Now my question to you is like, how many times will it print computing now? 0 or 2? 0, 0. Any 2s? A few 2s? Yes, the 2s have it. So something weird is happening here. But we modeled this stored unfinished as a side effect. And side effects you basically cannot reason about when they're not needed anymore, because like they're probably changing something outside the system. So they just keep happening until you stop them. But actually, modeling the computation as a side effect is taking a wrong angle at a problem. Why? Because computing a value is something you want to observe as well. If the value changes, you want to observe it. That's happening now. But also, if nobody is using it, you want to suspend it. So you want to establish that relationship, whether it's actually used by some side effect. So we're going to rewrite this a little bit. And we make this a computed property. And that means that MobX will automatically turn this into a computed property. So I remove the auto run. And instead of having a side effect like assignment here, it's now much cleaner. I have now an expression which I return from. So this is basically pure in the sense of it just depends on the to-dos collection. And now, if I enable this again, we basically didn't change the program anymore. It's still computing exactly twice. But if I now don't start that side effect, nobody is using that computed value, so it will never be used. And actually, I can even stop the side effect in the future by calling the return function. And now it will recompute computing while the side effect is alive. But as soon as the side effect dies and nobody else is using that computed value anymore, we fixed the problem. Different question. How many times will this compute? 2 or 3 times? So I toggle it to done, and I toggle it back again. Who says 2? 1, 2. Who says 3? Yes, the 3s are correct this time. Why? Because remember, everything is happening synchronously. So immediately after this assignment, MobX knows that the side effect has to execute, so it does. And then the next assignment happens, and then it toggles it back. So see, we print it twice because it changes twice. That's, of course, not what we often want. So that is where the concept of an action comes in. And an action basically it batches side effects. So I'm going to run this in a batch, and that means that like the side effects happen only at the end of the action. And so the question is, how many times will this compute? 2 or 3? Yeah, everybody paid attention, right? 2. But how many times will it print the amount of to-dos? 1, 2, 3. The correct answer is 1. You see, because something interesting is happening here. So the first time it always prints because that's the setup part. But then we change the done status, and then we toggle it back again. So in the end, here at the end, when the side effects are going to run, the unfinished status is still the same as it was before this whole action started. So it doesn't need to update UI again. So this is all nicely optimized out of the box for you. But now we can mess with the system, because now this is ideal, like, okay, the changes propagate only at the end of the action. So let's be nasty, and let's check what happens if I just print the unfinished to-do count in the middle of the entire action. Right, so the semantically correct output now should be 1, 0, 1, because like maybe sort unfinished is used in some computation, so we don't want to be reading a stale value. So let's see what happens. Well, that happens. Let's try again. So it still printed this unfinished to-do count correctly. So even though the updates can be postponed until the end of the action, if we require them earlier, we just evaluate them eagerly. And we can do that because this function is basically a pure computation from state. Like, it only depends on the state. It's not pure in a technical sense of the word, but I hope you understand what I mean. It's like just derived from the values. And so actually, it's also interesting to know that like this console.log, it causes this computation to happen. And then in the end, the side effects are also going to run, right? But it doesn't cause another computation anymore, because it already knows that this stored and finished is already up to date again, so that doesn't need to happen another time. Okay, one final thing I want to show you. And that is we're going to introduce a new property. we call it print. And we're only going to print if start.print is true, and otherwise we don't. And so let's run it and see what happens. We have only 2 computations. That's not much, right? Because like the first we get where it's from. This computation is happening of that initial auto run. And then we set print to false. And at the moment that happens, that causes this auto run to run again. But then the unfinished is not used anymore. And so if it's not used anymore, then it's going to be suspended again because nobody is needing it. Until we enable printing again. And then we should... Oh, I didn't enable printing. Sorry. You see, never trust comments. So now it's going to, after the print, actually this demonstrates it better. After the print, it's needed again, because now it determines the output again. So then it's going to reset up the dependency graph and run it. So actually, it depends at runtime based on what you're actually using and what branches you're taking to what it will be subscribing. So that's the kind of optimizations you really can't write by hand. That is like way too hard. But computing that is easy for computers. So conceptually, we have those things. We have the state, we have computed values, which suspend automatically when not observed. We have the concept of actions to batch updates. And we have reactions. And where computed values produce values, reactions produce side effects. And side effects we can reason about, so they are like the one that pull in the end all the values through the system. In other words, if you put it in a picture, there's always this kind of dependency graph. So in blue, there are the observables. There can be an arbitrary amount of computed values in between, but in the end, all the values propagate to some side effect. If no side effect is using a value, that value is not interesting to the system. It doesn't affect its output. And so that graph can become quite complex and quite deep. And the interesting way is if you have a graph like this, where there are 3 computed values, and one of them is computed onto other ones, then there's only one correct order of execution, which prevents double execution. So the only correct order to evaluate this is if the observable updates, then we want to update this one, because it has no other dependencies. Then we want to update that one. And only after that, we want to update that 4th derived value, because it depends on both of them. So it shouldn't start computing too early. And then if the output of this one didn't change, we don't want to run that side effect. And if the output of that one changed, we do want to run the side effect. And how that is done in practice is basically when a change is made, a topological sort is happening. So it means that I can actually, it's easier to show it in a presentation. So this didn't work well in Markdown, so I actually created a presentation. So the interesting thing, oh, this is not, sorry, that was the last slide. So suppose that this one changes. What we do is this one needs to run and that one needs to run, but they should run in the right order, right? Otherwise, the other one is going to print an old value. And so how do we avoid that? It uses topological sort. So if the first name changes, it's going to tell all its dependents that they are dirty. So they increase their dirty count to 1. That process is recursive. So full name is also going to tell all its dependents that they're dirty. So this now has a dirty value of 2. Now, when this, then after that, it signals a ready status. So the observable is ready immediately because it was just updating. And so all its dependents will decrease their dirty count. Now this one drops to 0, and that means that it's safe to execute this one. Nothing else it depends on is dirty. So it's going to recompute, and then it's going to tell its own dependents, I'm up to date now. That drops the dirty count of the auto run to 0, so that one can run again as well. And so we know for sure that everything is computed in the right order, and there are no double glitches. So if you want to build this yourself, this nicely summarizes it. And so we looked at a lot of complex semantics and cases and edge cases and optimizations. But the interesting thing is, like, from a user perspective, there are not that many rules to remember. Basically, MobX automatically tracks all observable data that is accessed during the execution of something that's being tracked. And also, the more computed values you have, or the more components you have, the more caching points there are for MobX to remember the output of a computation. So the faster your application will get. So, to conclude, how is MobX different from Angular and Meteor and Knockout and Vue, which basically all kind of have this very same idea, but yet a different implementation? And so one of the reasons for building MobX is that I did a lot of research on why people weren't happy about Meteor, for example. And the core reason was, like, it was unpredictable when things run twice. And so that's what I really tried to solve in MobX. And so first of all, the solution is independent. So you can use it with React. I just used it with the console. You also can use it with Angular. And that's actually faster than Angular's own algorithm. And the reason for that is that Angular depends on change detection. Change detection is, like, pretty expensive. But there's no change detection in MobX. There's only change propagation. When something changes, it notifies observers. But there's no hard comparison going on. No deep comparison. And further, it very explicit makes distinct concepts between side effects and derived values. Something you see in Vue as well. But pretty interesting, and it is also quite unique, is that everything is synchronous. And that really helps with debugging, because if something is not running when you expect it to, the cause of the rerun is still in the stack. It's like not running on a separate stack after a set timeout. No, you can just go back in your stack, and somewhere there should be changing something which causes the update. And in the end, because of the sorting, the amount of computations is optimal, minimal. So, for designing observable state, for managing state in the client, I think this is the best order of looking at a problem. And hopefully you have now enough knowledge to, like, build your own MobX. Spasiba.
Thank you very much. Do I have sound? Yes. Let's go in chat. I have some questions for you. Yeah, so we have only 5 minutes, so I think we take all like discussion, if not say holy work questions for discussion zone. Let's keep it here. Yeah, only urgent questions. And one of them, where do they use it in Battlefield 5?
It's used for the UI layer. So it's a pretty interesting story, actually. So, I mean, it's surprising that they use MobX, but it's also surprising that they use React in the first place, I think. And so they told me the story. And so basically, they're using React, but not React DOM. They have their own renderer, which renders components to the GPU, because React is such a nice programming paradigm. But then the problem was that they were re-rendering stuff way too much. Basically the same problem as I just have with circles and UI, circles and lines. And so they using observable to manage their UI state. So so that's the state of all the overlays and menus and those kind of things. So not like the 3D scenes, but like everything that's on top of that. That's managed in MobX.
Cool. Do you use immer inside MobX?
No.
Okay, so it's self-contained, right?
Yes, MobX is self-contained.
Nice. Not question, but more offer. So Evgeny says that maybe you should publish this micro implementation in order to have 200 bytes version. Is that possible? What do you think?
Yes, but you would quickly run edge cases where it's doing too much work. I kind of published a minimal version that does kind of work. It's called rval, but it's like not really a maintained project. It's just an experiment. But that is a really small implementation of the same algorithm without all the other stuff around it.
Can we use things like throttle or debounce in MobX?
No. And the reason, I mean, there's debouncing for side effects and such. So the answer in that sense is yes. And generally, I tend to say like, there's two kinds of reactivity. So the MobX reactivity is all about observable values that propagate through the system. The Rx kind of reactivity is about events and reasoning about the past. So if you're reasoning about events, and that's usually why you need throttling, then usually Rx is nicer, and like you can integrate them quite nicely. But like Rx is like about event streams, and MobX is about data change propagation.
Cool. Any way to do batch changes when you, I don't know, postpone something, for example, when you have to print high after some toggle? So to batch events.
So action batches, but that's like so side effects happen only after the outermost action finishes. And if you want to like have a fixed delay on it, on the side effects themselves, you can set a scheduler. So there you could like determine that you could introduce alternative timing behaviors.
Nice. And the last one, provocative question, a bit provocative. What are the downsides of MobX, and when immutable state approach could be more suitable, like in, say, other state management libraries?
Yes, I think there's a few cases where immutable is very interesting. So first of all, in any kind of like parallelism system, but luckily we are single-threaded so far in JavaScript. But beyond that, systems that reason about history, that really benefit from immutability, and systems that reason more about events that happened than about the state that the thing is in, really benefit from immutability. So I think that's the kind of trade-off. If you're like looking at a thing and you're interested how it changes over time, then I think MobX is nicer. If you're looking like about events, and you want to reason about the events that happened over time, then immutability is nicer.
Awesome. Thank you very much, Michel. And